Right. Well, as Sarah said, I'm going to be talking about uh, incredible fossil dinosaurs of China, particularly those that are preserved with soft structures like feathers. But before I talk about that, I want to introduce myself a little bit more. Uh, I got an early start in my interest in dinosaurs, like is so common with so many people. On the left, you see me at the Sinclair Dinosaur exhibit at the 1964 World's Fair. I was 11 years old. And those of you who have seen the movie Men in Black may recognize in the background the towers that played such a prominent role in that movie, left over from the World's Fair. And I had the good fortune of teaming up with a friend in middle school and then through high school named Tony Lessa, and we uh, got involved with finding many dinosaur footprints in New Jersey, and worked hard to convince the landowners, which they ultimately did, to donate the land for a dinosaur park, which it is today. Although it remains undeveloped, it is protected. And we found in that process thousands of dinosaur footprints. And I got really interested and involved in not just finding the fossils, but trying to understand the environment in which the animals that they represent were in. And I got very involved with things like ancient climate change and how ancient climate and modern climate is controlled. And so I've had many expeditions to different parts of the world. I've done large-scale fossil excavations in Eastern North America, but I've had projects in China, especially, which I'll talk about a little bit, and in the UK and in Morocco, and especially in the Western United States. And this way of integrating information from fossils and the ancient environments got me involved with what one of my graduate students calls paleoastronomy, in which we use rock cores collected by drilling rigs like this. And this has a project that I led in the Western United States to get at how ancient climate changes, and through that to the astronomical events and processes that control that climate change that can actually tell us about not just how the solar system evolved through time, but even get down to theories of gravity. But that's not what I'm going to talk about today. Today, I'm going to talk about dinosaurs and especially about dinosaur preservation. So the title of the talk is Incredible Feathered Dinosaurs of the Chinese Mesozoic. And Mesozoic, of course, is the age of dinosaurs from 252 million years ago to 66 million years ago. And uh, uh, on this picture, you see the very first non-bird dinosaur that was discovered with feathers. And on the right, you see a fossil cicada from the same deposit. And one of the things people do when they make these kinds of discoveries, it's normal for people to say, how can this happen? How can we get a perfect skeleton of a dinosaur with soft tissue and feathers be preserved? There must be something unusual. How can we preserve insects with color patterns and so forth? There must be something unique about the environment. And what I'll show today is that this kind of preservation is actually not unusual. So I'm going to give you the conclusions first. While the feathered dinosaurs of China are amazing, there's actually nothing extraordinary in the way they're preserved. That mode of soft tissue preservation is normal for certain kinds of rather common ancient environments, and they exist today too, such as very large lakes or restricted seas that are deep compared to their areas and have no oxygen at the bottom. However, what is extraordinary and why these fossils are from China is because of the extraordinary collection effort that the people in those areas have undertaken to find these fossils, so that even the most rare of fossils are found. So there are 6 parts to this. I'm going to talk about the importance of feathered dinosaurs, the extraordinary explanations. The style of preservation is not unusual. Talk about how the lakes are the environment in which they're preserved, the unprecedented collection efforts that resulted in these extraordinary finds, and why that's important to our future understanding of the evolution of dinosaurs and birds. So first, the importance of feathered dinosaurs. So we're going to talk about a variety of deposits in the world that are called Lagerstätten, which means basically place of storage. So we'll talk about first Solinhofen in Bavaria, which is a deposit of late Jurassic age, 155 million years old. Then we'll go to China to look at the Jehovah biota, which is early Cretaceous, about 125 million years old. Talk about the Yanlao biota at the same time, which is 160 million years old. The Eocene Green River, 50 million years ago. Then the Solite Cow Branch Formation assemblage, that's 220 million years ago in Eastern North America. And then I'll wrap up talking about Eastern North America and Massachusetts especially. Um, we're jumping around the world like this and different times basically to show you the themes of fossil preservation that are similar and preserve these remarkable features in the world. So we'll start with Solinhofen, which is certainly one of the most famous. Solinhofen is a city in Bavaria in southern Germany. The Jurassic limestones there have been quarried since Roman times for roofing slates or for paving stones or for architectural material. And the rock has to be quarried by hand. And this is actually a modern picture. That shows one of these quarries in Solinhofen. And because they're handled by hand, there are lots of fossils that are found in the process. And historically, the quarry workers or the owners of the quarries have used these fossils as a sort of side income. And over the years, over the centuries, remarkable fossils have been found. These are examples of a coelacanth up here, and below that, a stem gar named Lepidotes. Just to show you the complete preservation of these fossils. But when we look from space at this area, what we find is this industrial quarrying of this stone occurs on an immense scale. So you can see there's 2 kilometers down here, 2,000 meters, and every place that you see that's white in this Google Earth image are active quarries for this limestone. So here's the whole city of Solenhofen, Bavaria. So some of these quarries occupy areas as large as the entire city. So there's a lot of effort at collecting the stone and a lot of people looking at the stone and finding these very rare fossils. Well, just after Darwin's Origin of Species was published in 1859, one of the most famous fossils ever found in that area was discovered. On the left, we see that fossil bird, still the oldest known bird, Archaeopteryx. The first specimens were found in 1861, first a feather, then an articulated skeleton that looks like a roadkill, and then this 1874 specimen. In 1861, and now this is only 2 years after the Origin of Species, a little dinosaur was found called Compsognathus in exactly the same rock. One of the big issues that Darwin talked about in the Origin of Species was the absence of intermediates in the fossil record between one species and another, a prediction that came directly out of his theory of evolution by natural selection. Yet there were no such intermediates, which Darwin regarded it as a huge problem. But when these fossils were found, Archaeopteryx and the little dinosaur Compsognathus, and the concept of dinosaur already existed at that time from Richard Owen, the Thomas Henry Huxley, who sometimes called Darwin's bulldog because he was the guy who went out there and did the debates and pushed the idea of natural selection, Huxley realized that these 2 specimens were perfect intermediates between reptiles and birds. And this was the missing link, the word Huxley used, that demonstrated and corroborated Darwin's idea of evolution through time by natural selection. And Huxley in 1868, now we're 9 years after the origin of species, wrote the famous paper on the animals which are more nearly intermediate between birds and reptiles. And he, in that paper, actually talked about the Connecticut Valley tracks, and we'll come back to that at the end of this talk. And he illustrated a little sketch of Compsognathus, pointing out all the bird-like features in that little dinosaur. Well, fast forward now into the 20th century and the 21st century, and we understand from the basis of bones much better the relationships of various ancient organisms to modern organisms. We realize now that birds are, in fact, the direct descendants of dinosaurs. And one of their characteristic features of birds is, of course, the presence of feathers. Uh, and we know that the Saurischian dinosaurs, represented by modern birds, and ancient and extinct non-bird Saurischian dinosaurs like Tyrannosaurus rex, those Saurischian dinosaurs have near relatives in the Ornithischian dinosaurs, the two great groups of dinosaurs that are united together in the group called the Dinosauria. And then together with flying reptiles, which are not dinosaurs but are close relatives of them, called pterosaurs, they are grouped together in the group we call Ornithodira. All this is based on skeletal material and bones, fossil bones and modern bones. And then we have the modern crocodilians that are grouped in the group and the larger group called the Archosauria, the ruling reptiles. This arrangement of groupings of organisms actually makes predictions about what you should see in the fossil record. That's where these feathered dinosaurs become important. So we know birds have flight feathers. And it turns out that this group, near relatives of dinosaurs, but not dinosaurs, have filaments. They have all over their body that we can recognize are a kind of proto-feather. They're homologous to feathers. They're this developmentally in the embryology of organisms came from the same origin, but they don't have the plume-like shape that bird feathers have. They're simple filaments, and they are present all over the bodies of pterosaurs. Now, once you recognize that those features are present in saurischians, in modern birds, and in this extinct group, the Pterosauria, it makes the prediction that proto-feathers should be present in the common ancestors of those groups. That's a prediction. It's a scientific hypothesis. Uh, that prediction would argue that in all Saurischian dinosaurs there should have been feathers, and in Ornithischian dinosaurs there should have been feathers as well. But until recently, we had no corroboration from the actual fossil record of that prediction. But this is how you infer from things that are extinct something that we should find, and then we can look to see if we find it. So the prediction is that all dinosaurs should have some kinds of feathers. Now there were a number of brave souls in the 1980s that started to reconstruct dinosaurs. This is Deinonychus from the western U.S. from the early Cretaceous, and people like Greg Paul started to draw dinosaurs with feathers, even though there was absolutely no physical evidence that dinosaurs had feathers. In 1996, however, the remarkable find of this fossil, which I showed in my cover picture, Sonosauropteryx, was discovered, and it is completely covered in proto-feathers, similar to those in the flying dinosaur relatives, the pterosaurs. And there they are. There's absolutely no doubt that they're present, and this corroborates that hypothesis. No other kind of theory would predict this kind of fossil occurrence. So this animal comes from an assemblage of fossils from China called the Jehovah. And now I want to turn our attention to those and talk about the fossil preservation and the remarkable fossils from there. And with that, we'll also talk about fossil deposits that are in the same area that produce what's called the Yanlao biota that's actually older than Archaeopteryx. So let's take a look at some of those fossils. Well, here's an insect. This is a scorpion fly from the Yanliao biota 160 million years ago. And you can clearly see a color pattern on the wings of this beautiful fossil. This is a lace wing from the Jehovah biota 125 million years old. Again, you can see the color pattern on the wings. Uh, this assemblage, the Jehobiota, has a lot of fossil fish. This is a typical one called Lycoptera. Lycoptera, if you see this black dot here, this is the eye. It's black because it's preserving the retinal pigment in the eye. And the colors turn out to be a bit of an artifact, but I'll get back to that in a moment. Now, these assemblages produced insects for quite a long time, and there was a little local industry of quarrying these and selling the insects to collectors. In 1940, during the Japanese occupation of northern China, Japanese scientists described the first four-legged animal from these deposits, Monjurasuchus, which is a lizard-like form. And in this particular fossil, if we zoom in on the leg, you can see that the scales are preserved on the skin in addition to the bones. In the 1990s, we started to have the discovery of birds in these Chinese deposits. And in fact, when the first bird was found in these in 1987, it ended up being exported from China and sold at the Tucson Gem and Mineral Show in Tucson, Arizona for $18,000, which set off a gold rush, if you will, for these fossils in China, because $18,000 was more than a farmer would earn in a year, or maybe even in 10 years. And so this could provide a source of income if they could find these fossils. And here's an example of male and female fossil birds called Confucius Soreness, and again showing this soft tissue preservation. And here's an example from the Yanliao biota of a bird named after Thomas Henry Huxley, Anchiornis huxleyi, and you can see the spots on the feathers on the arms and the legs. And here's another one called Petapenna, which has enormous long feathers on the legs and on the arms. These are not birds, these are non-avian dinosaurs. And the microstructure of the feathers allows us actually to reconstruct the color patterns of these. And here's an example of a Petapenna in color. Some of the surprises that come from the soft tissue. This is an example of the shortest dinosaur name in the world, Yiqui, and Yiqui is a very strange dinosaur and was a complete shock because it developed flight independently of birds and had a bat-like membrane, but it was a true dinosaur and even has an extra bone in the arm to support this membrane. And this kind of creature came as a complete shock. Larger dinosaurs formed in the same deposit have feathers, including this Tyrannosaur eutyrannus. There's another one called Dilong from the same deposit that is covered with these filaments. This is below that is a small ornithischian dinosaur named Tianulong, also covered with filaments. So these dinosaurs had feathers. All the dinosaurs in these deposits had feathers. And pterosaurs, these relatives of dinosaurs, this is a small one from the Yanliao biota, are covered with these filaments, which are both straight filaments and branching filaments. So what do we learn from this? Well, this is really important because what we learn is when we look at the prediction made by this method of inference from the bones, we see that it's corroborated by the occurrence of these feathers in all of the dinosaurs that come from these deposits. So what does the rock look like from these deposits? Well, it's what we call microlaminated. That is, the layering of the rock is extremely fine at the scale of submillimeters, with no burrows going through the rock, no disturbance at all. And here's two examples from the Jeho biota of this rock and another example from the Yanliao biota. And this turns out to be a theme of these kinds of deposits, these very, very fine laminations, often with a high organic high organic content as well. So here's an example of one of those quarries. This is at a famous site called Sihiten, where a museum was built. These are igneous intrusions into this lake sediments, but you can see how the, 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 the lake sediments are these very, very fine layers. And it's in that deposit, that specific quarry, in which this fossil was found by a local farmer. And since then, many similar dinosaur fossils with feathers have come out of this deposit. This is one of the best. And again, you can see the eye, the retinal pigment preserved just like you can in the fish. So a museum was built on this site. And in the museum, you could see the rock layers and actual skeletons in place. And you can see a close-up here of this very finely laminated rock. And these darker orange layer are actually volcanic ashes. In 2014, my colleagues and I drilled a core at several of these dinosaur sites, and what we discovered in that rock core is, unsurprisingly, it was very finely laminated, but the rock was black, not white. And it turns out that the beautiful colors that we see in these fish are actually a consequence of weathering near the surface. This orange color is a mineral called jarosite from the breakdown of pyrite. The bone is black and the rock weathers to red, even though it was originally black. And here is a core that actually shows that. This is a cross section of the core, and there's one of these Lycoptera fish. The brassy color is the pyrite, and you can see that if the rock were fresh, you would never have those pretty colors. This site was opened up and a new museum is being developed on the site. This was from 2018. I don't know what the progress of the museum has been, but China puts an enormous amount of money into these museums and into the excavations of these fossils, and gives an enormous amount of money to the scientists for trying to understand them. This one's in the Jehovah biota at 225 million years old rock, and this one is in the Dahugo Museum in these rocks that are 260 million years ago. So what about explanations of this? Well, the fossils are so spectacular, surely there must be extraordinary circumstances. And extraordinary circumstances have been proposed. The most popular ones are the volcanic ash hypothesis. And I'll just read these very briefly. The most productive horizons are beneath volcanic tuff falls, which would have entombed most of the organisms in the water columns. The tuff layers, and these are ashes again, are strongly correlated with mass mortality events. Another one, the fine-grained volcanic ash that encloses the remains probably formed molds around complete skeletons, resembling the intact buried corpses in Pompeii. Here again, volcanic. 4 cycles of pyroclastic eruption in lake chemistry changed, geochemical redox proxies. The water column was completely oxic, and the lamination was due to other factors such as microbial mats or rapid sediment deposition. Or maybe it was a very shallow lake, and there were there were some other extraordinary circumstances that resulted in these preservations. That's normal for people to do. But they're all working within, as scientists tend to do, in these bubbles and just looking at that deposit and not about more general processes. So they think these fossils are so extraordinary, so therefore there must be an extraordinary explanation for their existence. But that turns out it's not actually unusual. So first deposit we'll look at is a famous one in the western US that's much, much younger, not from the age of dinosaurs, but from the age of mammals, that's 50 million years old, the famous Eocene Green River biota of the western United States. So there we are now. We've jumped to the western United States, and we're going to look at these deposits very briefly. Here's Wyoming, Idaho, Utah, and Colorado. These deposits were lakes that formed around 50 million years ago, and they existed for quite a few million years. The smallest deposit is called Fossil Lakes. That's in western Wyoming. And these turn out to be huge sources, potential sources of oil, but the rocks haven't been cooked enough to release the oil. They're what we call oil shales. But this fossil lake has had excavations in it since the 19th century. And today there are commercial operations that operate quarries, and they've been famous for a very long time for the preservation of insects. And you can see on these beetles color patterns just like we saw from China. There are whole fish preserved in these deposits just like we saw in China, even with the retinal pigments preserved just like we saw in China. Uh, Here's a lizard from the Green River Formation with the skin impressions, just like we saw from China, and a fossil bird with feathers preserved as well, just like we saw from the Yanliao and Jehovah in China. And the laminations in the sediments are similar as well. This is actually a fish. This is a fish turd, another fish turd, another fish turd in a microlaminated deposit. Well, what about the collection effort?
My apologies. I couldn't hear what you said.
Oh, for goodness sake, Siri. Siri just jumped in on my smartwatch. Not so smart. Anyway, um, so here's a commercial quarry which allow people to come in and collect fossil fish in the fossil basin in Wyoming, and they're excavating what's called the 18-inch layer. And you can see power equipment here, and you can see this big excavation in the background. But looking at it from space, you can really see the scale of these excavations. If you look closely at this image, these are pickup trucks. So these are large scale operations that are for commercial purposes to find these fossil fish and birds and lizards and crocodiles and mammals. And so tens of thousands or even millions of fossil fish come out of these operations. And if you go to any place that sells fossils anywhere in the United States, even Macy's, you will find specimens from the Green River Formation of fossil fish for sale. And I'm sure many of you have seen these. Now we're going to switch gears. We're going to move to a Triassic age deposit in North Carolina called the Triassic Solite biota. That's 220 million years ago. I had the honor of discovering these fossils. I didn't discover the site. That was discovered by quarry operators who were crushing the stone for lightweight aggregate. Here we are in Eastern North America. This deposit formed, as Steve Winter described, with the rifting of Pangea, and as it split apart, forming a series of basins that extend in Eastern North America, but are also in Europe and Africa, from Nova Scotia all the way down to South Carolina. And right now we're located we're talking from the Greenfield, Massachusetts, which is in the Deerfield Basin, one of these Triassic Jurassic basins. But the one I want to talk about is in the Dan River Basin on the North Carolina Virginia border. So here's how the quarry looked a few years back. This is when it was not active, but it's been active again. And you can see these layers tilting from left to right that were exposed by crushing for crushed stone, for quarrying for crushed stone. And in the process, right over here in the corner, a layer that was found by me that was turned out to be incredibly productive. And here you see a team from the Virginia Museum of Natural History collecting fossils from that site. And they've exposed the layers, and it's a pretty large scale operation, and they're looking for reptiles and insect remains. Uh, Here's one of the very first insects that I found in that deposit back in the 70s when I was an undergraduate. I did not name it. It was named by researchers later on, but as you can see, it's a perfect fly. The fossils look actually like somebody took a graphite pencil and wrote on slate. But they're often very small. You can see here's a millimeter scale, a single millimeter. This one ended up on the cover of Science magazine for a paper that I wrote in 1978 about these particular fossils. And there are many of them, many of these. We have thousands of insects from this deposit that are at the Virginia Museum of Natural History and at Yale University. This is a giant water bug, Triasonepa. uh, the oldest water bug known in the world. This is one of the most common of all of the fossils, this carnivorous water bug. And on the right is a small fly that was named after me by Blagodov and Grimaldi in 2007, but there are many flies from there. Now, one of the things you can do with these fossils is this is actually a skiff beetle, and here it is as it looks normally. But if you reverse the image, make a negative of it, it looks more like the other fossils. And this is a modern skiff beetle. But look at the scale at this. This is 1/10 of a millimeter here. Incredibly fine preservation. Here are some more beetles. You can actually see some of the color pattern on this one. This and the you can see uh, uh, the patterns in the eye. This is the compound eyes in this unnamed fly. And here's a thrip. And if any of you have house plants with thrips, you know how tiny they are. And you can see the little hairs on the wings here, and this incredibly nice. This how fine the preservation is. And here's a scorpion fly with a little bit of a color pattern. This only has a spot on the wing here, but this is similar to the scorpion fly that we saw from the Yanlao biota. And yes, there are reptiles preserved. The most common one is this lizard-like form named Tanatrachelosa, which are known from males and female specimens. And you can tell from the reproductive organs. And here's a specimen. This is the back and the neck, and it's a little scattered. The skull's a little bit scattered, but the skin is preserved both on the leg here and on the arm. Here's a close-up of the skin. We can't see any scales, which leads us to believe that it actually had smooth skin. This is on the arm. And here's a baby. Again, this is 1 centimeter, and the skeleton is preserved with skin all over it. Now, this rock is very black when it's fresh in the middle of the quarry, but up near the land surface where it's weathered, it turns a light color. The rock turns light, the bone remains black, the pyrite around the skeleton weathers orange, and you end up with the same color pattern that we saw with the Jehovah biota in China. So this is an example of weathering enhancing the color contrast. What about the rock itself? What does it look like in cross section? Well, just like the examples from China and the Green River Formation, it's microlaminated with these very, very fine annual laminations, just like we saw in Green River and in the Chinese deposit. And just to bring home how similar these deposits are for each other, I'll show you some spiders. Here's an example from the deposit in North Carolina from 220 million years ago. Here's one from the late Jurassic, 160 million years ago, the Lanao biota. Here's one from the Jehovah biota from 125 million years ago, and here's a 50 million year example from the Eocene Green River Formation. 4 examples, 4 similar styles of preservation. Note the color, by the way, on the legs. On the Triassic one. So these aren't the only 4 examples I could have picked, but we have them 3 examples from the age of dinosaurs from the Mesozoic, 1 example from the age of mammals from the Cenozoic. What unites these things? What's the common theme? The preservation of all these things is extremely similar: soft tissue preservation, color preservation, and so forth. What's the common theme? So it turns out the theme is, and this is also true for Solinhofen, which isn't a lake. It was a restricted sea, but it works basically the same way. That these are productive bodies of water that were deep relative to their surface areas. And that's what resulted in what's called chemical stratification of the lake waters, which results in that extraordinary preservation, which really isn't so extraordinary. So this brings us to the common theme of all of these deposits, the stratified lake model. So what happens in a lake that's deep relative to its surface area is the wind, which mixes the water, doesn't have enough energy to mix all the way down to the bottom. So you end up with an upper layer that's well mixed and a lower layer that's poorly mixed. Now, if the water's cold, like in Siberia, like with Lake Baikal, which is a giant lake, which is super deep, 1,600 meters deep, the bottom layer is poorly mixed, but because the lake is cold, the organic productivity is relatively low, and as a consequence, there's not much organic matter sinking to the bottom, and bacteria don't use up all the oxygen, resulting in a low oxygen mixed zone. There's oxygen right down to the bottom of Lake Baikal. But in Lake Tanganyika, which is almost the same proportions as Lake Baikal, like Tanganyika's in East Africa, you end up, because of it's much warmer, you have lots of biological activity, the organic matter sinks to the bottom, and there the bacteria consume all the oxygen, so you end up with no oxygen and a boundary layer that's called a chemocline. So if you happen to be a fish that dies and sinks into the bottom, there's nobody there to eat you. So you settle down to the bottom and you're preserved in your entirety. Also, there are no large animals cruising through the sediment, so the laminations end up being preserved completely. If we look at modern lakes, these are 4 examples of modern lakes. One's in New York State that produces these microlaminations because it's chemically stratified. Lake Basumptwe in Ghana is actually a fossil asteroid impact, but it's one that's relatively modern, only a few million years old, and those microlaminated sediments are produced, and there's actually fossil fish from cores in this modern lake, although I don't have an example of one for photograph, unfortunately, but I know they do exist, that were found in rock core and the sediment cores from the lake. Here's Lake Van in Turkey, and here's Lake Malawi in East Africa, all of which are producing these beautiful microlaminated sediments which preserve whole fish. So that's what the lakes do. And if you're in the Black Sea, which is a restricted marine basin, you get the same kind of style of the preservation of laminae, but of course it's the Black Sea is still there. We can't go and find fossil fish or fossil organisms, but they're presumably there. So if this is a common style of preservation of laminae and fossils that occur in these lake sediments, why is it that we only have these feathered dinosaurs, or almost only have these feathered dinosaurs, from these Chinese deposits? Well, I would argue it's the unprecedented collection effort that results in extraordinary finds. So basically, this comes down to what's called the species rank abundance. So this is a kind of a nerdy term scientists use for a very common pattern in life on Earth. Basically, any place you go in the world, if you're in a lake, if you're in a forest, if you're in a field, and you census all the organisms present, what you find is that there are a few very common species of organisms and lots of rare ones. So when you take species number one, that's the most common one, its rank is 1 in terms of abundance, it plots over here. The second most common one plots over here, the third most common one here, and so forth. And you just take the number of organisms and plot them against the order of their abundance. And what you find is most of the species in any of these environments are at the tail, if you will, of this curve. So let's take a look at an actual example. So these are Australian desert lizards. Over 20,990 individuals were caught, and they're ordered. There are 2 most abundant forms, and you see for these 2 species, there were over 2,000 specimens found out of this 20,990. Then there's a third, which is almost 2,000. The next most common one, the fourth, is down to about 1,200. 1,000 for the fifth, less than 1,000. You can see, and as you go down this curve, you're getting fewer and fewer individuals. And to get this 67 species, which isn't that many species, you have to collect 20,000 individuals on average. Now, of course, you could be very lucky and just find this very rare one first, but you're unlikely to find a second one. This is just probability, right? The probability of you, if you got 100 specimens from this assemblage, chances are most of them would be these guys, and you'd have virtually nobody down here. Very, very important. So to find rare things, you have to collect a lot of stuff, thousands and thousands and thousands. So let's take a look at another kind of graph here. We have time of publication on this axis and the number of dinosaurs described. So the first dinosaurs were around 1824, and then through time, the number of dinosaurs have been increasing. And this census only goes to 2008, but this curve is still steepening with more and more dinosaurs discovered. Virtually every week, a new dinosaur is named. The lining here refers to this area in North China, both the Yanlao and Jeho biotas, and you can see them starting to appear in the 1980s, and that's actually the birds that are found there. And here are those same birds. They're increasing in abundance, all fossil birds on this diagram here. And you see that these birds in China just made their appearance back here in the 1980s and becoming more common through time. Let's look at this in a little bit more detail. The Jeho fauna in China was first described by an expatriate Columbia professor named Amadeus William Grabow in 1923. The first four-legged animal found, the first reptile found in this deposit was described in 1940. In 1962, the Jeho fauna was renamed the Jeho biota. The first bird wasn't found until 1987, Soreness, and that's which was sold for $18,000, and this things just took off after that in that area. Cathiornis was the next bird discovered in 1990. Confucius Soreness was discovered in 1993. The first feathered non-avian, non-bird dinosaur was discovered in 1996. The Dahuo biota was discovered in 1998. Another dinosaur, another dinosaur, another dinosaur, another dinosaur, 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 whoops, getting away from myself there. So what happened? Well, people became really energized about that $18,000. That's what happened. And farmers who could work on the land in these rural areas, they couldn't work on them in wintertime. They have a winter like northeastern US. It gets cold. You can't farm then, but they could find fossils. And they opened quarries to find these fossils and to sell them. And here's an example of one of those quarries in a place called Wambanjigo. And that's actually where we cored. We actually did a rock core up here, right through this whole deposit. And this quarry was opened for insects and for pterosaurs. But they were hoping to find dinosaurs. They found pterosaurs. Those sell very well too. And there were enormous numbers of these quarries opened in the region. So if you stand on that quarry that I just showed you a photograph of that was opened by farmers and look across the valley, you see all of this rock showing up here. These are all quarries opened by farmers for these fossils. And if we look at it from space, from a Google Earth image from 2010, and it's changed now, but this white layer, which you see here, so these are vast stream valleys, right? This is a village of Wambanjigo. These are ridges. This white layer that you see going along the landscape are actually quarries opened by farmers for these fossils. You can see the layer going around here and coming around this way, and then it goes below the surface and you don't see it anymore, but it pops up here again, and then the farmers have opened up all these quarries. This is what's been done in these regions, and hundreds and hundreds of quarries you can see from space. And that's actually where we got our cores from in those areas there. This is my colleague, Professor Jining Shah of Nanjing, and he's standing in front of an open mine that was dug by these farmers. These are not legal; these are illegal. The government does not want the farmers to do this because does this look safe to anybody? That's why Professor Shaw looks so worried standing in front of this, because who knows how many people died in the effort to collect these fossils over thousands of these mines opened illegally. Not all of them are open pits like we saw at Wanbanjiko. Many of these are tunnels into the sides of hills that go in for hundreds and hundreds of feet. So these fossils end up getting transferred to middlemen. The middlemen then give them to shops or sell them online, and all of that sale is for fossil fish it's okay, but for reptiles and dinosaurs it's not. Now they're prohibited in selling those, but it still occurs on the black market. This is a picture that I took of what's called the ancient street in Chaoyang in this area of China where these fossils are collected. And all of the shops along the street deal in fossils. And in fact, this is one of the fossil shops. You see some Westerners wandering around here wanting to buy some fossils. All of these are fish from these excavations from the farmers. And you can see there's a left and right half because the fish have been split, and there are hundreds and hundreds and thousands of these fish for sale. You can also find fish like the little Lycopter I showed you earlier for sale in North America. Here's another one of these stores selling these beautiful fossil fish. And you can imagine there are 50 or so stores on that street, all of them selling this fish. Those are not the only places that the fossils are sold from these deposits in China. And farmers have collected these by the millions. To give you an example, how rare the fossils are. Some fossils are from these deposits that are found. I'll show you the case of this little lizard-like form called Felosaurus. Felosaurus comes out of these quarries in the thousands. There are thousands of these. You can actually buy these little things, again, all over the world. They fetch a couple $100 a piece, which is pretty good. But so many millions of these have been found that the rarest of the rare of the rare are found. Here's an example of a juvenile Felosaurus from this deposit, and it's a little unusual. It's unusual because it has two heads. The frequency of this kind of dicephaly, as it's called, which are really a kind of conjoined twins that survive, the frequency of dicephaly in reptiles is about 1 in 500 million. And when a two-headed turtle is born, or a two-headed lizard is born, you usually hear about this. 500 million is not all that many for people to look at, but they do make news. Occasionally, a mammal is born with dicephaly, or even a human. In humans, the frequency is 1 in 5 billion. So, how many fossils do you have to collect to find one of these? Millions, millions of fossils have to be found to find these rare things. So that's what I mean by extraordinary collection effort. So now we come to the conclusions, and we'll wrap up shortly. While the feathers dinosaurs are amazing, there's actually nothing extraordinary in the way they're preserved. Their mode of soft tissue preservation is normal for these kinds of lakes and seas that are deep compared to their area. What's extraordinary, really extraordinary, is the collection effort that's been put into finding these things with thousands of people making excavations that can be seen from space. Now, the last point I want to cover here is why this is important to further progress. We already saw how the feathered dinosaurs of China produced corroboration of the hypothesis that feathers were common in all dinosaurs. But what about the origin of dinosaurs? What kind of feathers were present in the earliest dinosaurs? When did these feathers appear in pterosaurs? Well, we don't know, because the older dinosaur deposits have not been collected in this effort. In Eastern North America, our Triassic and Jurassic age deposits are famous for the preservation of dinosaur footprints. On the left here, you see the famous Holyoke footprint preserve, which preserves many footprints of dinosaurs, but especially those of Eubrontes giganteus, which was first named in 1836 by Edward Hitchcock, as was mentioned by Sarah Doyle and mentioned by Steve Winters. But there are also lake deposits, well, deeper lake deposits. Actually, the footprints are preserved in shallow lake deposits, but the deep lake deposits produce beautiful fossil fish, just like the ones I described from Solite or from the Green River Formation, and especially those of China. And here we see a coelacanth. This is from Turner's Falls, very similar to coelacanth I showed you from Solinhofen, Bavaria. Here's a fish called Semionotus, very similar to the stem gar I showed you from Solinhofen, Bavaria. Paleoniciform fish related to sturgeons from Turner's Falls. These three fish are from Turner's Falls. This is one is from Connecticut, but it's also known from Northampton, Massachusetts, called Tycholepis. Here's the Turner Falls deposit at the Turner's Falls Dam, and it's these laminated deposits that produce these fossil fish. This is what they look like in cross section. This is an example of the East Berlin Formation, which is the same age as this and the same deposit really as we saw in Turner's Falls, but it's called a different name there. It's called the Turner's Falls Formation. An example from the Shuttle Meadow Formation, an example from the Booten Formation. The fossil fish from these deposits have been known since 1812, actually, and they've been collected, but on a relatively small scale. Here's an excavation in Durham, Connecticut in 1900 that produced a few hundred fish, and here's an example quarried by my friends Nick McDonald and Bruce Cornett in 1973, and that produced a few thousand fish. So that's the scale at which these fish have been collected, and they're beautifully preserved. They're absolutely extraordinarily preserved, very similar to what we saw in these Chinese deposits. And there are even insects in these deposits. Now, the promise of these deposits was recognized all the way back in the 1800s. And Thomas Henry Huxley, who we saw talking about the missing link between dinosaurs and birds, was aware of the promise of these deposits. So this is what he said in 1868. He knew about Hitchcock's 1836 Eubrontes giganteus. The important truth with which these tracks reveal is that the commencement of the Mesozoic epoch, bipedal animals existed that had the feet of birds and walked in the same erect or semi-erect fashion. These bipeds, either birds or reptiles, or most probably both, and it can hardly be doubted that a lithographic slate of Triassic age would yield birds so much more reptilian than Archaeopteryx, and reptiles so much more ornithic than Compsognathus, as to obliterate completely the gap which they still leave between reptiles and birds. And so even Huxley in the 1800s recognized that these Triassic and Jurassic deposits of the Connecticut Valley, of even Turner's Falls, could produce intermediates between reptiles and birds. So were a similar effort expended in these Eastern North American deposits, we would have our own feathered dinosaurs. Do we have hints that this might be the case? We do. Here are two examples of theropod dinosaur teeth from these same laminated deposits. So they were there and their remains got into the lakes, and it's just a matter of collection effort and time before we have our own feathered dinosaurs. So that's what I wanted to say about these extraordinary Chinese feathered dinosaurs and what they mean for our future understanding of dinosaur evolution and discoveries. So I'll open it to questions now. I'm going to stop sharing. The fact that Sarah has not jumped in.
Here, and I'm here. It's Jonah.
Okay, Jonah, and told me I had 15 minutes left. Makes me think that we may have a tiny technical problem. I see Sarah's there, but she's muted. No. Any questions?
So I have a couple hand raised. Mark, I will allow you to talk. and there we go. Mark, go for it.
Olsen, how are you doing?
Hi, Mark Meck. What's your whole name?
Mark Agostini.
I thought that was you. Well, good to meet you, Mark.
Yeah,
we need to Zoom together.
Yes, we do. Yes, we do. Great talk. So I just had a question for the dinosaurs that would be roaming around, the Connecticut River Valley. Where on their bodies do you think feathers would be? Would it be on the feet or along the back of the dinosaur? I'm just thinking.
Yeah, so that's a good question. So actually, there's some direct evidence for that, believe it or not. But I think they'd be mostly over their bodies. Depends on the group. The theropods may have been, especially the small ones, may have been completely covered in filaments. Well, I don't expect any true bird-like feathers to be found. So expect the feathers of the small ones all over their bodies, but not their legs, not the lower legs, and not their feet. Then in the case of the ornithischian dinosaurs, the small relatives of duck-billed dinosaurs, we'd anticipate most of their bodies to be covered, but not their legs, and maybe not most of their tails, but on on parts of their tail, especially the top, would anticipate rather long feathers. And there's one specimen at the Benesky Museum that looks like it actually has those filaments preserved, in addition to a very detailed impression of the scales along the tail, which look remarkably like those of a small ornithischian dinosaur from the mid-Jurassic, from Siberia, called Colonodromus, which also has very long filaments on its body and on its tail. So depending on the dinosaurs, there'd be slightly different arrangements, but most of the small ones would have them on most of the bodies. Maybe the largest ones, like something like Dilophosaurus, would have had a more restricted number of filaments, because as you get larger, the advantage that these filaments give the animals, why they have them, is for insulation. And even if you're in the tropics, it gets a little chilly at night, and it's important to retain that heat if you're an active animal. But as you get larger, your thermal inertia can, just the mass of your body can hold on to that heat. You don't need as many feathers, and feathers are something like hair that you need to keep clean, and so there's a cost to that. So large animals in warm areas tend to lose their hair or their feathers. Ostriches are only half covered with feathers, and elephants, the African elephants, almost lost all their feathers. But baby African elephants, baby African elephants have more hair, and Asian elephants, baby Asian elephants, are downright hairy and look like little woolly mammoths. In some cases, there's quite a bit of variation, individual variation. So that's an answer to that question. Basically, it would be varied, but most of them would have some feathers for sure.
Wonderful, thank you.
Sure.
Great, let's jump down to the chat. Kathleen asks, what is the difference between filaments and feathers?
Filaments look more like hairs. The structural difference between a hair and a feather, especially these filaments, is that hairs are solid, like our hairs, and feathers are hollow. That's the big difference. And even as we know, the feathers of modern birds are hollow. That's why you can use a goose feather as a pen, because the hollow quill can hold the ink. But even the simple filaments, these so-called protofeathers, were hollow as well. So that's the filaments differ from modern feathers of birds in being very simple structures, but we see in these feathered dinosaurs this whole range, from filaments to branching structures to very simple modern type of filaments, to the modern structures with barbules that link all the parts of the feathers together. That whole range is present in the feathered dinosaurs of China, but only the modern types survive now, of course. So that's the difference between filament and a modern feather.
Great, and look, we have time for a couple more. Robert Nash, I have just promoted you and asked you to unmute. So you should be all set in a second, if you can just unmute. There we go.
Yep, I got it. Thank you, Paul. Fantastic presentation. My question has already been answered. I just wanted to speculate or hear what the speculation was on the evolution of feathers. What advantage it presented to the dinosaurs? Was it more effective than the filaments? Is that it?
Well, the filaments were the first feathers, and their main advantage is insulation, and that is still a fundamental important thing for modern birds. That's why they can survive in cold areas. It's completely because of their insulation. So the filaments provided that. Now the question you're getting at is, why did modern types of feathers evolve? And the modern type of bird feather actually appears before flight does. In birds with short arms, and dinosaurs with non-bird dinosaurs with short arms have modern types of those feathers on their arms while still retaining the simple filaments on their body. There are two main functions that those would serve in a non-flying animal. One is for display. You could, and ostriches do this. They're not flying, but they wave their arms around for display all the time. The other function, which has not been talked about, but it's a theory of mine, and I think it's a good theory, is that the dinosaurs that have these feathers on their arms, relatively short feathers, short arms, the function of those is in fact a type of aerodynamic function, but it's to brake. So if you watch an ostrich running at 40 miles an hour, when it tries to turn, if it wants to turn right, it sticks out its right arm, and that acts like a parachute, slowing it down, and then it turns right. If it wants to turn left, it sticks its left arm out. If it wants to stop, it sticks both arms out. And this is what ostriches do when they're running at 40 miles an hour. And the non-avian dinosaurs with those adaptations are the ones we see early on with those modern type of feathers, which have big surface areas. And so that's what I think these short-armed earlier dinosaurs that have modern type feathers, what they evolved for. So the feathers are primarily for insulation. They get co-opted by increasing the surface area for aerodynamic purposes while running. And then, of course, once the bigger surface area is there, they can be co-opted for lift and for flight. And then you get the modern condition. But modern flightless birds that have reasonably long arms use them for when they're running.
Fantastic. Thank you.
By the way, I recognize the name Nash. Are you part of the Dinoline Nash family?
No, not at all. I'm Steve Winter's brother-in-law.
No kidding. All right. Well, very good. Thanks.
Great. Let's see if we can fit in one more from Simon, who I think we heard from in the last session. So I just promoted you again. So if you can, let me see. There we go.
How did feathers dinosaurs in the dinosaur time protect themselves from big meat eaters like the T-Rex?
So we know that that's a very good question. So just to repeat that, how did the small dinosaurs protect themselves from a bigger meat eater like T-Rex? They ran very fast. And some non-bird dinosaurs may also have been able to fly with big enough feathers on their arms. So those are good ways to get away from something like T-Rex. But baby T-Rex had the same problem of being eaten by a larger meat eater too, and they also had feathers, and they also had very long legs and would have run away from the meat eaters. They could run very fast. And if you're as big as Tyrannosaurus Rex, you really can't run that fast because your leg bones aren't strong enough. But you can run fast enough to catch other very large plant eaters to eat those. Great question. Great question, Simon.
Thank you.
So we are a minute over. Paul, I don't know what your schedule is. We have a couple more.
I can hang on here. It's no problem. Great.
So to everyone else, thank you for coming. If you need to leave, it is technically our time, but also feel free. It sounds like we can do a couple more. So give me 1 second. Michael, I am giving you permission to talk. And I will ask you to unmute.
Michael, you there?
Oh, can you hear us, Michael? Says you should be all set.
Why don't you check? This is Michael Shiner. Why don't you type your question into the chat window?
In the meantime, Steve Winters has a question. I read that some dinosaurs evolved bat-like leathery wings, but that turned out to be an evolution dead end. Correct?
Yes. So that was Yi-Kui, which I showed earlier. There are actually several of them. They're called the Scaniceropterids, and Scaniceropterids apparently evolved these bat-like wings, even though their body was only covered in filaments. So they didn't get to use the they didn't use their feathers for aerodynamic purposes. Instead, they developed these bat-like membranes, and they don't. So in pterosaurs, which superficially look like they have bat-like wings, those wings are actually composed of filaments themselves, which are joined together to make the membrane. And those have the advantage of being arranged in the same orientation as feathers. So if you get a cut in them, the aerodynamic function doesn't fall apart. And in a bat, it does if you cut the wing, because that's a membrane stretch. And the Scaniceropterids had a similar membrane to bats, and they that was not as a good of a system as modern birds. In modern birds that fly, every single flight feather is a separate aerodynamic structure. It's a separate airfoil. So that is an incredibly efficient structure, because the whole wing makes an airfoil, but then the individual flight feathers make airfoils as well. So that's a better structure than a membrane. So basically, the Scaniceropterids probably couldn't compete with birds. Their membranes were too delicate compared to a bird wing. And I see a question from Will Sillen. Will, are you there? What's the difference between filaments and scales? Well, that's a really good question. For quite a while, there were some researchers who actually argued that scales and feathers were not homologous. They weren't developed from the same embryonic structures. But now we know that's wrong, that the embryonic structures of birds are homologous with those of lizard scales. And the scales that are on birds' feet are homologous to the scales on living reptiles, and feathers are modified scales. And one theory is developed because of the work on this Siberian form Colonodromus, which has many different types of protofeathers on it, but some of them are what are called bristle scales, which are a plate-like scale, which is what scales normally are. They're like little plates and not a tube, and they have these filaments extending off of them. And some of those filaments in some parts of the body are arranged into circles. So you have an incipient tube instead of a plate. And then in other parts of the body, there are actual filaments that look like all those things can join together in a tube. So that's how we think we got from scales to feathers. And you can see these bristle scales are already acting like insulation even before the filaments that are homologous to modern scales are present. And in deep time, it turns out that the embryonic structures that give rise to scales are called placodes, and those are also present in mammals that in our development give rise to our hair. So when we had a common ancestor all the way back in time, back to about 350 million years ago, that common ancestor probably had scales that diverged then to give you hair on one side, which are solid structures, and feathers in reptiles, and birds, which are reptiles, which are tubes.
Great. And then Michael has written a question in the Q&A. And also, Judy, I see your question. We'll finish off with that.
There we are, Michael. As you know, we find lots of phytosaur and Hypsognathus, etc. Why does it seem so hard to find dinosaur bones? Well, Michael, in East North America, during the, as you know, during the Triassic, dinosaurs were less common than they are in the Jurassic. So we have lots of Brachychirotherium and things like that. But we don't have much in the way of dinosaur bones. And we do have tons of Hypsognathus. But Hypsognathus, I think, are like gopher ecological equivalents that may be predisposed to being preserved by dying in burrows. I think that's part of the why Hypsognathus is so common. So in the equatorial regions in Pangaea, we find like in North Carolina, Virginia, instead of Hypsognathus being common, you get these little mammal-like relatives, which really do like little gophers, Boreogomphodon, which again, probably preserved in burrows. I suspect that if we could collect enough bones, we would start getting the dinosaurs. But as you know, it's so hard to find bones in these Triassic, Jurassic deposits. And by the way, for everyone out there who's still listening, I don't think that's because the bones themselves are rare. It's because the rock in the Western US and places where you find these great skeletons, the rock weathers very easily and is softer than the bone, leaving the bone sitting on the surface. While in East North America, these same rocks, same age rocks, have been cooked deeper in the earth and are very, very solid. So we only see the bones in cross section, which makes them much, much harder to find. But I suspect they're actually a lot more common than we think. It's just a matter of finding where the bones are abundantly preserved. In the deposits that have all those Hypsognathus near where you live, Hypsognathus is almost all we find. Even there's like one tooth, right? And then one plate off a crocodilian's back, and that's it for non-Hypsognathus. And yet we've gone through tons of rock there, and because of the housing excavations. So I suspect it would be just a matter of time.